So from the computer program, we can find the data, and we actually did the experiment for like 5 times. Then we pick up the most accurate data, which is this one. So here we got time, position, and velocity of the free fall of the ball. And 0.6 is the time we drop the ball, and so that's our initial time. Then at the initial time, the ball's position from the motion detector is 0.185, and its velocity is 0 because it's like we're still like holding the ball and drop it, so it's supposed to be 0. That's right. And 0.85 is the time it hits the ground. So the graph is going, so it's going like straight line. Position is 0.552. Velocity is 2.156. Then we can use our equation to get the average power and instantaneous power. We use 2 different equations for average power and instantaneous power. So for average power, we use is average power equals to work over time. So which is mgh. H is the distance the ball drop. So h here is the position difference. So it's 0.442 minus 0.185. And the time difference is 0.85 minus 0.6. Then we get our average power is 1.43 joules. For the instantaneous power, we use the equation P equals to Fv, and V is the final velocity, F is the mass, the weight of the ball. And we get the mass of the ball is 0.142 kilograms, then we times G times 9.8, and then we get, we use this here, final velocity, we use 2.156, that's when the ball hits the ground, and we get 3 joules. So we get some really interesting data and like calculations. So that's actually approximately twice. So the instantaneous velocity is actually approximately twice of the average power. But we want to prove why that happens. So here we come to our proof for that. So the average power is work over time, which is mgh over time. And we use the free ball equation for, so h equals to 1/2 gt squared. That's when we drop the ball at v naught equals to 0. So we can use this equation. And then we just do some math, and we plug h into this h, and then we get the final average power equals to mg squared t over 2. And here we do the instantaneous power using Fv, so mg times Fv. And then we plug into another free fall or distance equation we used before. That is V final equals to V naught plus AT. And A here is just the gravity, so that's G, A is G. And V naught, we get here, is approximately 0, so we can just ignore this. So we get mg times gt equals to mg squared t. So we can see we got like the proof why we have approximately twice the amount of average power. That is the instantaneous power. So because instantaneous power is mg squared t, and the average power is mg squared t over 2. So yeah.